The perception of time when traveling in a rocket is an intriguing topic that intertwines the realms of physics, particularly the theory of relativity and human psychology. Understanding how time is experienced and measured in a rocket involves exploring both the relativistic effects predicted by Einstein's theories and the subjective experience of astronauts. This episode delves into the scientific principles, psychological aspects, and real-world experiences of space travel to illuminate how time passes in a rocket. Einstein's theory of relativity, comprising both special relativity and general relativity, fundamentally changed our understanding of time. According to special relativity, time is relative and can vary depending on the observer's velocity. This phenomenon, known as time dilation, becomes significant at speeds close to the speed of light. Special relativity. When an object moves at high speeds, close to the speed of light, time slows down for that object relative to an observer at rest. This means that a clock on a fast-moving rocket would tick more slowly compared to a clock on Earth. To illustrate time dilation, consider a hypothetical scenario where a rocket travels at 90% of the speed of light, approximately 270,000 kilometers per second. According to special relativity, time aboard the rocket would pass slower compared to time on Earth. If an astronaut spent 1 year traveling at this speed, significantly more than 1 year would pass on Earth. Lorentz factor. The extent of time dilation can be calculated using the Lorentz factor. At 90% the speed of light, the Lorentz factor gamma is approximately 2.29, meaning time on the rocket would pass roughly 2.29 times slower than on Earth. General relativity introduces another aspect of time dilation, which occurs in the presence of strong gravitational fields. This effect, known as gravitational time dilation, means that time passes more slowly in stronger gravitational fields. For astronauts in orbit, this effect is minimal compared to the velocities involved but becomes significant near massive objects like black holes. Gravitational influence. The closer an object is to a massive body, the slower time passes relative to a distant observer. This is why time runs slightly faster for satellites orbiting the Earth than for clocks on the planet's surface. Human time perception is not only influenced by external factors but also by internal cognitive processes. In space, astronauts experience a unique environment that can alter their perception of time. Factors such as isolation, altered day-night cycles, and the monotonous environment of a spacecraft can impact how astronauts perceive the passage of time. Circadian rhythms, the body's internal clock, are influenced by the 24-hour day-night cycle on Earth. In space, where this natural cycle is absent, astronauts can experience disruptions in their circadian rhythms. The International Space Station, ISS, orbits the Earth approximately every 90 minutes, resulting in 16 sunrises and sunsets each day, which can further complicate the maintenance of regular sleep-wake cycles. Sleep management. Astronauts use artificial lighting and scheduled sleep periods to help regulate their circadian rhythms. Despite these measures, maintaining a consistent perception of time can be challenging in space. The isolation and confinement experienced during long-duration space missions can also affect time perception. Without the regular social interactions and environmental changes typical on Earth, astronauts may find that days blend together, leading to a distorted sense of time. The psychological stress associated with prolonged isolation can exacerbate these effects. Monotony and routine. The repetitive nature of daily tasks and the lack of new stimuli can make time seem to drag on for astronauts. Conversely, busy periods with high levels of activity can make time seem to pass more quickly. Astronauts aboard the ISS have shared their experiences regarding the perception of time in space. While scientific measurements confirm the effects of time dilation due to the high orbital speed of the ISS, approximately 28,000 kilometers per hour, the subjective experience of time varies among astronauts. Astronaut reports. Many astronauts report that the structured schedule of work and exercise helps maintain a sense of normalcy. However, they also note that periods of intense activity can make time seem to fly, while quieter periods can make time drag. For missions to the Moon or Mars, where astronauts would spend extended periods away from Earth, understanding and managing time perception becomes even more critical. The psychological effects of long-duration missions include the potential for increased feelings of isolation and the need for effective strategies to cope with altered time perception. Proposed missions to Mars, with round-trip durations of up to 3 years, will require careful planning to ensure astronauts can maintain a healthy perception of time. This includes maintaining regular communication with Earth, providing diverse and engaging activities, and managing sleep cycles effectively. As we plan for longer and more distant space missions, understanding how time is perceived in space will be crucial for mission success. This involves designing spacecraft and habitats that help maintain a stable perception of time, including appropriate lighting, varied activities, and social interaction opportunities. Advances in technology may offer solutions to manage time perception in space. Virtual reality environments, for example, can provide immersive experiences that break the monotony of space travel. Wearable devices that monitor and regulate circadian rhythms could also help astronauts maintain a healthy perception of time. Providing psychological support for astronauts will be essential in managing time perception during long-duration missions. This includes training astronauts in coping strategies, offering regular psychological check-ins, and ensuring they have access to mental health resources. The passage of time in a rocket, influenced by the principles of relativity and human psychology, presents a unique challenge for space travel. Understanding both the objective scientific effects and the subjective human experience of time is crucial for the success of future missions. By addressing the factors that influence time perception, we can ensure that astronauts are better prepared to handle the psychological and physiological demands of space travel, paving the way for humanity's exploration of the cosmos.